Hello. Let's talk about bijections between a set and itself. They're called permutations. So let's imagine a set and then a map from X to itself. Let's call it permutation. If this map is bijective or invertible. Let's denote somehow the collection of all such. So let's call it S of X for symmetric group on X. That will be the set of all permutations of X. So yeah, it's mostly going to be mostly interesting for us when X is a finite set, and we can make it a bit more concrete than just an arbitrary finite set. Let's just think of it as a finite set of first n natural numbers, not counting 0, starting with 1. So then we will just call the symmetric group of that set as sub n. So there will be permutation of n first natural numbers. And the main exercise here will be counting these permutations. It will be as good as counting permutations of any n-element set. So let's just determine the number of elements in it. Well, the process of counting will be really the process of writing these permutations down, recording them. So how can we record a function? We can record it by recording all its values. So here is an arbitrary input for our function sigma, an arbitrary element of X, and we just need to record the answers. Well, they're what they are. Sigma on 1, sigma on 2, sigma on n-1, sigma on n. So that is tabulating, if you like, a function, listing all its values. And every function will be among these answers, so will be encoded by the collection of values. So now we have to imagine the condition of being bijective, so being injective and surjective for a finite set, and a map between it and itself is enough to just see that this map is injective, that no two different elements go to the same answer. So that is the condition we have to obey, imagining our function, imagining its values. And we have to count all possibilities. So let's just start by counting how many ways we can create the first answer. Well, any element in X can appear as the first answer. So we have n elements, we have n possible answers for the first value. After we have the first value chosen, then choosing the second counting possibilities for the second value, we have to exclude the first one. So of all n elements in our set X, we have to take away 1, and then we'll have n minus 1 possible answers for this second value. Then continuing, you could see the pattern. So the third one will be chosen in a number of ways, which will be a total number of elements, but not equal to the first and the second chosen, so n minus 2. And all the way till the say last two, that will be chosen, possible to choose in 2 ways, and after that we will already collect n minus 1 elements and use them as answers, and so the last element will be determined, will be whatever is left. So that will be the number of choices for each separate value if we choose them in this order. And since now the answers are, so these numbers are independent, these choices are independent, the numbers can be multiplied when we count all possible tables of functions. So that will become the product of 1 and 2 and all the way down to n. And that product is called n factorial. And that is the quick formula for counting the number of permutations. And let me just look at the sort of small size example, the first size example, which is interesting. If we just have one element set, we cannot do anything interesting with it. We have to keep it fixed, and that will result in 1 factorial permutations of this one element set, and that is rather trivial. So let's look at the next in line permutations of 2 elements. 2 factorial is 2, and we should have 2 permutations. Permutations are maps from x to x, so we'll just record them by drawing them. So here is my 2 element set. Upstairs 1 copy of x, downstairs is another copy of x. This is my source, this is the target. The picture for the identity map will be just this. So to say, first element 1 in the set x goes to itself, element 2 goes to itself. So that is one definitely bijective invertible map, definitely permutation. I could have another when I just send 1 into 2 and 2 into 1. And that will be it. So I can now complete the list because I counted them, they should be 2 and I have 2. And let me recall a fact about permutations, being bijections. They are closed under composition. So if we look at the permutations as a part of all maps, we can compose maps from x to itself, and this is a subset of invertible, of bijective maps, and is closed under the composition. So we could apply this property, say, to this example and see how the composition works on these 2 elements. So write the composition table, similar to the multiplication table. I'll just put all possible permutations as labels of my columns and rows, and then in each position I'll just record the composition of, say, this following that. So in the picture here I will have to start with this map and then follow with this. And pictorially, starting with one map, so F, that is a picture of the composition of F first and then G. So I have some map which does something to my elements, and then I have a picture for G. It's in this box, and I just need to concatenate them in this matter. So that will be producing the picture for the composition. And following this rule, well, it actually doesn't matter what the rule is, because the answers will not depend on the way we compose, on the order we compose, but in large examples they will. So identity composed with anything will be just giving us that thing. It's the identity property. The only interesting computation is to be done here when we compose what is called a transposition. That is a permutation which maps 1 into 2, and, well, really it's in this picture. I would better just use the picture. 1 goes into 2 and 2 goes into 1. So that composed with itself is identity, because 1 goes first into 2 but then brought back into 1, and so is 2. So the answer here is the identity, and we have this composition or Kelly's table of the symmetric group on 2 elements. So that is a first example. In the infinite sequence, you are invited to write down all 6 permutations of 3 elements and to write 6 by 6 table of composition on them. That is an interesting exercise. I'll see you later with more.